Properties of the modulus. The following properties of the modulus should be known, although many of them are readily apparent. The first one, that mod z bar is equal to mod z, we've discussed that before. Let's suppose z was equal to 3 plus 4i. Then z bar, or z star, is equal to 3 minus 4i. So it should be fairly clear that mod z here would just be the square root of 3 squared plus 4 squared, which of course is 5, and mod z bar is equal to 5 as well. We saw that with a complex number and its conjugate, that they're reflections in the real axis. And clearly the vectors therefore are the same length. Mod z squared is equal to z bar. We could use the same ones. If I do z bar, that is 3 plus 4i, 3 minus 4i. And that is going to be 9 take away 16i squared. I squared is negative 1, so that's 9 plus 16, which is 25, which is the same as 5 squared. Now these ones are fairly apparent. The modulus of z1 times z2 is equal to the modulus of z1 times the modulus of z2. It's easy to remember rather than being apparent, I think. The same thing is true of a quotient. The modulus of z1 divided by z2 is equal to the modulus of z1 divided by the modulus of z2. And that is provided that z2 is not 0, of course, because we can never divide by 0. And then an extension of this one is that if we have a whole string of complex numbers multiplied together, and we take the modulus of that, then it's equal to the individual moduli being multiplied together. And an extension of that is if all of those numbers are the same, then we have mod z to the n, which is the same as having mod z then raised to the power n, and that works for n as a member of the natural numbers. Remember, those are the counting numbers, 1, 2, 3, 4, 5, and so on.